This is the first lecture of Chapter 22 dealing with the second law of thermodynamics. We may recall the 0th law of thermodynamics defined temperature, and then the first law of thermodynamics was conservation of energy. Change in internal energy is equal to whatever we add to the system, whatever heat is added plus whatever work is done on the system. However, if we actually looked at nature, we would observe that really only certain energy transfer processes actually take place. So even though the first law allows conservation of energy, really we see that only certain processes take place. So we need to have more constraints than just the first law. So we have the second law of thermodynamics, which states that the total entropy, which is disorder, of the universe increases in all natural processes, so that as a progression of time, entropy in the universe will increase. And the kind of process that will occur is one in which entropy increases. So we can actually look to see that and determine what direction the process will go. This is the second law of thermodynamics, and it is a law of nature. So with this law, we will be able to establish what actually does occur and what won't occur in nature. A good example, illustration of the second law of thermodynamics is what happens with heat engines. Implication of the second law is that heat engines have limited efficiency. In a heat engine, we're going to take energy, heat energy from a hot reservoir. We're going to perform some work, and what's left over we're going to expel to a cold reservoir. So we're going to take in energy from a hot reservoir, do some work, and expel energy to a cold reservoir, and that's going to be our heat engine. It's going to be a cyclic engine, so our change in internal energy will be equal to 0. So whatever engine is performed by this, or whatever work is performed by this engine, will have to be equal to the net heat exchange. So whatever we take in minus whatever we put out, that extra heat difference is going to be equal to whatever work we can do by the engine. So the work by the engine is equal to our net heat exchange, and the work of the engine then will be equal to whatever we take in from the hot reservoir minus whatever we lose to the cold reservoir. That is a net work done by a cyclic engine. On the PV diagram, it's going to be the work done by the engine. It's going to be equal to the area enclosed by the cyclic path on the PV diagram as you go clockwise. So the net work done by the engine will be a clockwise area enclosed in a positive sense, and negative if it's going counterclockwise. Positive if clockwise, negative counterclockwise. So just the opposite of what we were doing as far as work done on the system. This engine is trying to do work outside of the system. It's trying to do work on other things. So it's still the area enclosed, but positive if it's clockwise. We define, with a triple equal sign, we define the efficiency as being the work performed over the heat input from the hot reservoir. We can write that as the difference between the heat input from the hot reservoir minus the heat expelled to the cold reservoir over the input of the hot reservoir, or simplify this as 1 minus the heat expelled to the cold reservoir divided by the heat taken in by the hot reservoir. This is our heat engine efficiency. And I can see it as work performed over what we got from the hot reservoir. In other words, it's what we hope to gain, which is the work performed over what we got from the hot reservoir. So efficiency is the ratio of your objective over your input, what you hope to gain, your objective, over your input, in this case from the hot reservoir. That is our efficiency. With a little bit of algebra, we can manipulate this definition of efficiency, and using the definition of work, and we have that work is equal to the efficiency times the input from the hot reservoir, or equally, we can say that the input of the hot reservoir is equal to the input to the cold reservoir divided by 1 minus the efficiency, or work is equal to the efficiency times the input to the cold reservoir over 1 minus the efficiency. These are all manipulations algebraically of what we just saw previously, and any of these equations could be useful in dealing with heat engines. Let's try an example. Here's a problem. A particular engine has a power output of 5 kilowatts and an efficiency of 25%. If the engine expels 8,000 joules of heat in each cycle, find, first of all, the heat absorbed in each cycle. So our Q sub C is going to be what we expel, 8,000 joules of heat, and we have a relationship of that to our heat input, Q sub H. That is, Q sub H is equal to Q sub C over 1 minus the efficiency. 8,000 joules is what we expelled. Our efficiency was 25%, so 1 minus that would be 0.75. 8,000 divided by 0.75 is 1.07 times 10 to the 4 joules, or 10,700 joules. What is the time required for each cycle? Well, we know if we have power, we're doing work per time. So by definition, power is work per time. So time would be equal to work divided by power. And if we're putting out 5 kilowatts, a watt is a joule per second, we would have that our time is our work, which is our heat input minus our heat output, or what we take in from the hot reservoir minus what we expel to the cold reservoir. That's our work divided by the power in terms of joules per second. So we have 10,700 joules minus 8,000 joules over 5,000 watts, joules per second, and that gives us seconds. 0.53 seconds. So the time for each cycle is approximately half a second. We can re-express the second law of thermodynamics in several forms. And one form is the Kelvin-Planck form, which states that it is impossible to construct a heat engine that takes in energy by heat from a reservoir and performs an equal amount of work. The way this would look like is, here's our heat engine. We have an input from the hot reservoir, and all that energy goes into useful work in the engine, nothing expelled to the cold reservoir. It's impossible for this to happen. So this is a statement that we can't have work of the engine that is exactly equal to whatever we take in from the environment. This will never happen. This would require us to have 100% efficiency. Q sub C cannot be equal to 0. Our efficiency cannot be 100%. That would violate the second law in this Kelvin-Planck form. Heat engines can be run in reverse. If we do this, we have ourselves a heat pump. This is not a natural direction of energy transfer. It's not natural to go spontaneously from a cold reservoir to a hot reservoir. So this requires an input of energy in the form of work done on the system. So we must put energy into this device, and this is called a heat pump. We're going to extract energy from a cold reservoir and expel it to a hot reservoir. Maybe we want to make the hot reservoir hotter, or maybe we want to make the cold reservoir colder. But this requires work input to do this. Examples: a refrigerator. If we are extracting energy from the cold reservoir and trying to keep it cold, that could be our refrigerator, but that's going to require electrical energy to come in, and hence we're going to expel that energy to the environment. Same thing with the air conditioner. Here's another form of the second law in the Clausius form. Energy does not transfer spontaneously by heat from a cold object to a hot object. So we cannot have heat come from a cold reservoir, go through our engine, and get expelled exactly into a hot reservoir without the input of work. In this engine, no work is required. This would be impossible to have this occur. This is an impossible heat pump because we can't have the spontaneous flow from cold to hot. The effectiveness of a heat pump is described by what we call the coefficient of performance, or COP, C-O-P. Similar to thermal efficiency for a heat engine, in cooling mode, your objective is to remove energy from a cold temperature reservoir given an input, which is your work. So you have an objective over your input. The coefficient of performance in a cooling mode requires some supervision. So we have a COP. All right. So our coefficient of performance in cooling mode is what we hope to get or hope to gain, which is to extract energy from a cold reservoir over what we got, which is the work input to our system. So again, just like efficiency, it's what we hope to gain over what we got. A typical refrigerator will have a coefficient of performance around 5 or 6. In heating mode, your objective is to take in heat from a hot reservoir over your work input. So you're going to take in heat, make your hot reservoir hotter. Maybe you wish to warm the room. And that divided by your work input is your coefficient of performance. Generally, your hot input is higher than your work input, so this will have a value generally greater than 1. Note that a coefficient of performance is not the same as efficiency, so you can have a coefficient of performance greater than 1. Of course you can. It's what you are exchanging over what your work input is. So, summary of the second law of thermodynamics. The total entropy disorder of the universe will increase in all natural processes. Implications of this: there is no 100% efficiency possible. The increase of disorder demonstrates the advance of time, a direction to the process. So if you had 2 moments in time, you could measure the disorder at each moment, and whichever one has the more disorder came at a later time, because that is the flow of the universe. So a process is going from less disorder to more disorder, and that is the progression of time as we know it. Heat will flow spontaneously from hot to cold, not the other way around. With regards to engines, this means, at least from the first law, that you can't get more energy than you put in. Conservation of energy says that whatever you put in is the maximum change in internal energy you can possibly get. And in nature, you also find from the second law that you can't even break even. There's no 100% efficiency, so even though you take in energy, you can't use that energy usefully in 100% efficiency. You can't even break even due to entropy. So here's an application or imagination of an application, a perpetual motion machine. Imagine this. We have water falling down some certain height, so we've got potential energy being transferred into kinetic energy of the water motion. At the bottom of this waterfall, we have a water wheel, and we're turning the water wheel. As the water wheel is turning, we're moving a coil within a magnetic field, hence generating a changing magnetic field and a changing motion of an electric field. So we generate electricity. We use that electricity to power a motor, and we use that motor to run a pump. And the pump will pump water from the bottom of the reservoir to the top of the reservoir so that it can fall again. For this machine to work, it cannot work perpetually. because for it to work perpetually, we'd have to assume that energy was conserved every step along the way. There would be no energy lost to friction. There would be no sound, because sound is energy, so there'd be nothing lost in every step of the way. You wouldn't be able to hear anything. No loss to friction. That would violate the first law of thermodynamics. Also, it would violate the second law, because if there's no exhaust heat from any of these processes, no heat engine, no energy lost, then you would have 100% efficiency, and that's not possible. So you couldn't have 100% efficiency, you couldn't have 100% conservation of energy. A perpetual motion machine is impossible. No perpetual motion machine will ever be invented. So if you have designs on one, either involving gravity, which is actually a force, not a source of energy, even involving gravity or magnets or lever arms or that sort of thing, that kind of machine will never work in a perpetual motion device. You can never get more energy than what you put out. So you can't have a above unity engine. That won't work either. That definitely won't work. And perpetual motion won't work either. If you have designs on this and you don't believe me, a very good place to go is on the web, a place called the Museum of Unworkable Devices. So go ahead and Google that, or Bing that, or Yahoo that, whatever search engine you use. Find the Museum of Unworkable Devices. And there you'll find a plethora of machines designed over the history of time that look like they should work on paper, and they don't. And the museum has a very good explanation of why most of those machines don't work. Here is Sadie Carnot, named Sadie by his parents so that he would be tough. He figured that if you're named Sadie, you're probably going to get beat up by the other scientists around there, and you're going to get tough and you're going to persevere. So all the paintings of Sadie Carnot show him with a Band-Aid on his nose, where he broke his nose from all these fights. But we'll paint that out. French engineer, only lived to the age of 36, so maybe somebody got to him eventually. First, to show the quantitative relationship between work and heat. Coincidentally, devised the Carnot engine, which actually has his name. A heat engine operating in an ideal reversible cycle, now called the Carnot cycle, between two reservoirs, is the most efficient engine possible, because every step of the way is reversible. So we're going to look at a cycle where if you go through it quasi-statically and establish equilibrium every step of the way, you can actually reverse that and go back. So you can't do better than that. So if you're going through any kind of reversible cycle in this manner, it's the best possible cycle you can have. So the efficiency of this cycle will set an upper limit on the efficiencies of all other engines, because all other engines cannot do better than this, where you have reversible cycles every step of the way. Here's the design of the Carnot engine. We have two adiabatic and two isothermal processes, all of them reversible in a quasi-static way. So you go one point, establish equilibrium. You could also go back if you wish, but continue through these processes. By reversible, there are no dissipative effects in each stage of the cycle. We have an isothermal process at our hot temperature from A to B, and an isothermal process at our cold temperature from C to D. As we go from A to B, we might take in heat because we are actually expanding as we go from a lesser volume to a greater volume. So this engine is doing work. And so to maintain the same state, the internal energy state, at the same temperature, we'll have to take in energy. So we take in heat energy during this process. Then we go from B to C adiabatically. Adiabatic means no heat exchange. But in this case, as we look at this PV diagram, we are expanding. Our volume is greater at point C, so this engine has done work going from B to C. And if we don't take in energy as heat, then our internal energy must decrease. So we're going from a hot temperature to a cold temperature, and our change in internal energy will be negative. Then we go from C to D. We're compressing, so our volume's getting less. We're going to have to expel energy in order to maintain a constant internal energy in our system as work is being done on our engine. Then we continue to change our volume from D to A in an adiabatic process. No heat exchange there. So we're going to have to, our internal energy is going to have to go up as work is being done on our engine, and hence our state will have to change as we go from the cold temperature to the hot temperature. So this is our Carnot engine. 2 isothermal processes, 2 adiabatic processes, a cyclic engine. Change in internal energy is 0 overall, and the work done by the engine is the area enclosed by this cyclic process. The best engine possible. All real engines are less efficient than this Carnot engine because all real engines will have some kind of irreversibility to them. So they can't be totally reversible like this engine is. Here's another look at this Carnot engine. Going from A to B, we have isothermal expansion. We're connected to a heat reservoir, so as we maintain our internal energy as constant, at a constant temperature, we're going to have to take in heat internal energy because adiabatic means we have no heat exchange. So our internal energy will go down and our temperature will go down. We have an isothermal compression, so we're going to maintain our internal energy at a constant temperature. That means we're going to have to expel heat in order to do that as we're doing work on our system. And then we have a adiabatic compression. No heat exchange with the outside world, but we are compressing, doing work on our system. Hence our internal energy should go up, and our temperature will go up as a process of that as well. In fact, we'll go back to our original high temperature. The efficiency of a Carnot engine, efficiency Carnot, is what we hope to gain over what we got. And what we hope to gain is work done by our engine, and what we got was the heat input from the hot reservoir. That's equal to 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir. And that is the Carnot engine efficiency, and that is the best possible efficiency we can get between 2 temperatures established in our engine. These temperatures must be in Kelvin. So if you use this Carnot efficiency equation, you must change all of your temperatures to Kelvin to use this equation. This is the best you can do. So all Carnot engines operating between these same 2 temperatures will have this same efficiency. The efficiency will increase when the difference between the cold and hot temperatures will be expanded. However, it's impossible to have an efficiency of 1 because that would either require that our hot temperature was infinitely large, not possible, in order to make this fraction 0, or that our cold temperature was absolute 0 in order to make that fraction 0 in that case. Either one of these is impossible. It's impossible to have an infinite hot reservoir, and it's impossible to have an absolute 0 cold reservoir. So 100% efficiency is not possible even with our Carnot engine. Theoretically, we can run our Carnot engine in reverse. This would constitute the most effective heat pump possible. So our Carnot heat pump coefficient of performances, COPs, 2 of them. Alright, we'll get rid of those. In heating mode, our coefficient of performance in heating mode is what we hope to gain over what we got. What we hope to gain is to add heat from our heat reservoir, and that's going to require work. So in heating mode, we're going to put heat into our reservoir from hot, and that's going to be our temperature of the hot reservoir over the difference in temperature of the hot reservoir minus the temperature of the cold reservoir. That is our coefficient of performance in heating mode. In cooling mode, our coefficient of performance is what we hope to extract from the cold reservoir over whatever work input we have. So what we hope to gain over what we got. And that is the temperature of the cold reservoir over the temperature of the hot reservoir minus the temperature of the cold reservoir. Let's try an example of the Carnot efficiency. A steam engine has a boiler that operates at 500 Kelvin. The heat changes water to steam, which drives a piston. The temperature of the exhaust is that of the outside air, about 300 Kelvin or room temperature. So we have a cycle between two temperatures. What is the maximum thermal efficiency of this steam engine? We have a hot reservoir and a cold reservoir. And our maximum efficiency is the Carnot efficiency, 1 minus the cold temperature over the hot temperature. 1 minus 300 Kelvin over 500 Kelvin is 1 minus 0.6 or 0.4. The maximum thermal efficiency of this engine is 40%. Determine the maximum work this engine can perform if it absorbs 200 joules of thermal energy from the hot reservoir during each cycle. Well, our input is 200 joules. Our efficiency is 0.4. So our work is going to be 0.4 times that input, or 80 joules. So this engine can actually perform at maximum efficiency 80 joules of work, given that our input was 200 joules. That concludes the first lecture in Chapter 22 on the second law of thermodynamics and the concept of entropy